So here's the cliffhanger that I left you at the end of our last exciting episode. One of these characters is telling the truth, the other is lying. How do you know the difference? Well, certainly not just by looking at the organisms. Okay? Um, Particularly with genetic data, if two organisms that are very, very distantly related happen to have the same mutation and the same adenine changes to a thymine at the same position in the DNA, you're never going to be able to tell by looking at the present day genetic sequences. However, there's a nifty principle that we can take advantage of to figure out which of these characters is telling the truth. And basically the way to sum it up is this. Different liars will tell different lies, but all truth tellers will sell the same truth. Okay, so if you've got different characters that lie, different homoplasies, they ought to all be telling different lies. Okay, but your synapomorphies, your true synapomorphies, all ought to tell the same story. They ought to tell you about the same evolutionary history. In other words, if you keep looking at more and more characters, what will happen is that all the synapomorphies will keep pointing toward the same correct evolutionary history. They'll keep supporting the same true phylogeny. The homoplasies will also start piling up, but each homoplasie that comes along will be pointing at a different wrong hypothesis. It'll be leading you toward a different wrong phylogeny. And eventually what happens is as you keep collecting characters, the synapomorphies, more and more of them start pointing toward the correct hypothesis, and they sort of outvote, they overwhelm all the different wrong lies that the homoplasies are telling you. So this is what we do. We look at what each character is telling us, and here they all are. Two species have the derived character state from mammary glands, so that this trait claims they belong together in a clade. Lack of fins put these six together in a clade. Fur puts these two together in a clade, and on and on and on. This one, we can ignore it. Goodbye, because it doesn't really tell us anything useful. But all of these other ones, as far as we can tell, each one on its own seems to be a synapomorphy. At least, we've got these shared derived character states for each of these remaining 8 characters. What do we do now? Well, the simplest thing to do is start at the bottom. Where is the biggest clade within this group? Because that's probably somewhere down near the root. And here it is. This is the biggest clade that we've got. So we're going to put that down at the bottom here, and then we're going to start nesting clades within it. Because remember that what you can do with clades is you can nest them within one another. If you can fit one clade entirely within another, they don't disagree. So for example, claws or nails here has the chimpanzee, the crocodile, mouse, pigeon, and lizard. That nests within this one. Okay, this clade lacks the salamander, but all the others could form a subclade within this clade. Let's see how that looks. So we start with lack of fins. That's the character that has the biggest, the synapomorphy that has the biggest clade. And what that maybe implies is, okay, when we put claws or nails in here, or lack of gills, they actually have the same, they have the same synapomorphy, they have the same synapomorphic group. What that implies is that all of these belong to one lineage, and that the salamander kind of split off on itself after this point in time. Okay, so those nest within one another. There's no disagreement there. So, okay, we haven't found any problems yet. Well, okay, warm-bloodedness, yeah, okay, that does not disagree with this character. It would nest just fine in here. And mammary glands and fur, those two characters would both nest just fine within that. So, okay, we haven't found any problems yet. Let's see, carrot and scales, that nests just fine into here, and gizzard nests just fine into there. Okay, except there's one problem. Again, if the pigeon is most closely related to the crocodile, it cannot be most closely related to the mouse and the chimpanzee. So these two traits disagree. These two character states disagree. In the same way, if the pigeon is more closely related to the crocodile and the lizard than it is to the mouse and the chimpanzee, these two character states, or these two characters rather, disagree. At this point, what we do is we invoke this principle called parsimony. There are two possible explanations for what we're seeing here. Okay, one is that this is the true evolutionary history over here. Really, the pigeon is more closely related to the crocodile than it is to anything else. But after it split off from the crocodile, it evolved to be warm-blooded. And so that's why it ends up looking like it belongs in this group over here. The other possibility is this, that the pigeon really is the closest relative to the chimpanzee and the mouse, but after it split away from this lineage, it evolved a gizzard and it evolved carrot and scales, and so it looks like it belongs in this clade and this clade. Okay, I'm oversimplifying things a little bit here, but there are other ways in which you could get this pattern, but all of them basically involve the same thing. If this is a true statement about the evolutionary history of these organisms, then you had to have at least two evolutionary changes for the pigeon to end up in these two groups over here. Whereas if this is the true evolutionary history over here, you only had to have one coincidence, one homoplasy, to get the pigeon over here. Parsimony is a principle that suggests that, look, go with the simplest explanation. In this case, there were either two coincidences or one. The idea that these are both homoplasies requires two coincidences. The hypothesis that this is a homoplasie only requires one coincidence. And so we lean toward this being the correct hypothesis, and we toss out this trait as a homoplasy. I mean, in reality, when you've got a vote of 2 against 1, that's not really strong evidence that this is the correct hypothesis about the evolutionary history, and this is not. What you really want is lots and lots and lots of traits piling up on this side and very few over on this side. But just for the purpose of this demonstration, basically what I want to show you is that this is how essentially synapomorphies will end up outvoting homoplasies. Okay, once we throw out this character, do we have any more disagreements? Okay, once we decide that, okay, warm-bloodedness must have been a homoplasy, do we have any more disagreements? Okay, this nests within this nests in here, and this nests in here. Okay, we don't. So basically what you're seeing here is the true evolutionary tree. We've completely reconstructed the evolutionary history of this group of organisms. And let me show you how this works by walking through what we've reconstructed. Okay, so we've got this group here, then this group here, then it splits. This group goes off to one side, this group goes off the other side, and then we get the crocodile and the pigeon together. Let's see how that plays out through evolutionary time. What does this imply? Well, what do we know to begin with? We know that there's a lineage at the root of this tree that we're trying to reconstruct that leads to all 7 of these species. Okay, and so What's our first character, the biggest character, the one with the biggest, the largest number of the largest number of organisms that share the derived trait? It's lack of fins. Okay, well, lack of fins, let's see, that suggests that all 6 of these belong together in a clade. Oh, but it leaves out the perch. What that implies is that down here at the root of the tree, there was a split. And that the fish split one way, the lineage leading to the modern fish split one direction, and the lineage leading to these species went the other direction. Okay, our next character, the next largest clade that our characters are telling us about, is claws or nails. Lack of gills, by the way, is telling us about the same clade. It says that the chimpanzee, the crocodile, the mouse, the pigeon, and the lizard all belong together in a clade. Okay, so we look at that. Oh, okay, the salamander isn't part of either of those. What does that imply? Well, it implies that the lineage leading to all these species splits, and the salamander went one direction. Okay, one of these, after the speciation event, one of these lineages led to the modern day salamander, and the other one leads to all of these species. Next, we have 2 characters that tell us about the splitting of this group. One of these, you've got mammary glands and fur suggesting this clade, and you've got keratin scales suggesting this one. Well, that splits this group right in half. Suggests that this lineage here went through a speciation event. You have one daughter lineage that's going to lead to this clade, and another daughter lineage that's going to lead to this clade. Okay, there's our split. Here our organisms move apart. Okay, this is the last character we have to look at, gizzard. Suggests that the crocodile and the pigeon are one another's closest relatives. The lizard here gets left out. What that implies is that the lineage leading to that set of descendants splits. The lizard goes in one direction, and the 2 other organisms go in this direction. This is the lineage that evolves the gizzard. Okay, so we get this split. And that's it. That's all the characters we have. Well, we do have to do some more splitting here, but that's trivial because we know that these are all different species in the present day. We know that at some point in the past, they split apart from one another. And it's got to be basically between this point in time and the present day organisms. So here they go. We split them apart. And we follow through to what we see in today's world. So one character at a time, we split this clade away from that lineage, then this clade split away based on another 2 characters, then this group here split away from this one based on things like mammary glands and fur and keratinous scales. The presence of the gizzard implies that these 2 belong together, and so it split away from this. And then all the species separate, and here we are. We have completely reconstructed the phylogeny for this group. Ta-da! One thing that you should keep in mind is that whenever a phylogeny is reconstructed, it's a hypothesis. Okay, they're not facts. And as we gather more data, often phylogenies have to get shifted a little bit. We get more genetic data, and oh, okay, all of a sudden looks that species A is really most closely related to species B. At first, when we started getting in genetic data, it caused massive shifts in a lot of the evolutionary understandings that we thought we had. Because we were getting all of this new data, in some cases told us completely new things. We learned a lot about the tree of life once we start getting that data. As people gather more data and as computer algorithms can more powerfully crank this data to make these evolutionary trees, we find that we're adjusting the trees less and less. So we're homing in on the true tree, but we can never be 100% sure that we're there. If you can, you always want to double check a tree with other sets of data. So for example, if you've built a genetic or a tree that's based on morphology, that's physical characteristics, let's compare that to a phylogeny that's based on DNA sequences. Do they tell you the same thing? Well, yeah, pretty much they do. There are a couple of, there are one exception here. The genetic data say that the turtles belong here as the close relatives of the crocodiles and birds. That's not what the morphology says. I wonder what happened there. That's another mystery that poses another question to solve. But for the most part, you see that these two phylogenies support one another, and that's very encouraging.